morning, everyone. This is week 2. I hope you have been accustomed to doing things now. And I want to begin by sharing my screen. That is not what we are going to be talking about today in the form of a lecture. But since I've been busy yesterday sending you emails around things that have to do with OSBOL, I thought I would probably just begin by showing some things there and making sure that we have all a good understanding of how the functionalities there. So does everybody see the screen that I'm sharing? Can James just confirm? I know, or whoever is. Yes, okay. So this is what it looks like. It might look slightly different from your point. This is the instructor's view of it. And from, you know, the reason that we're using this one is because I'm used to it, and it has got some simplicity, some intuitive nature to it. And so we'll continue to use it. And you are all familiar with what it has. But when I send a mail, it's got its own mail functionality. So that's what you see at the right corner here. And this one, you can set it up so that you would get it forwarded whenever I send a mail to your WSU email address, so you can read it. And the way you do that is by going to your settings. And so if I go click here, I can see there are 3 or 4 things there, including how many mails that I haven't read and things like that. But the place where it says setting, if you click there, then you get to see different things. For example, if you want to upload your picture, so when some people use the posts, then they would see that will be one option to do. I have done. But what I wanted to show you is if you scroll down when it says email notifications, there are different boxes that you can check, and I've checked all of them, which means if somebody sends a OSBOL notification to my email address, then I would get a notification in my email address. If something is posted on the dashboard, I get a notification. If somebody has got a post or a feed or some other reply, then or discussion that has happened by email, I get. Because I wanted to keep an eye on things, I have checked them all. But you may want to see which ones you care about and make that selection so that you get notified. That's one thing I wanted to point out. The other thing I wanted to point out is when the activity feed, this board, the dashboard, is a good way to communicate. And so far it's been mainly, and it's not very surprising that I use it. But if there are things that you would like to point out, especially now that we are in a distance learning environment, I think I would encourage you to use it. And so when you post a message, you can choose who you want it to be seen, everyone, or you can say instructor only or TA only, and that way you can choose. But most of the time, maybe you may have something that you want to share. So I want to relax a little bit on how strict I am on this one to allow you to share things that you may find useful. Whenever I post, what I do actually is post it to the class, which means all of you who are there would get it, but I also check this box so that you get an email in addition, or not in addition, but you get an email version of it. So instead of coming and checking this website for what has been posted, you get it immediately. And I have made it a habit to have something to say right after lecture if something's posted and things like that. So by checking this one, I make sure that you get emails. That's how you have been getting. So the rest of the things on the right, you are familiar with them, and so I don't need to tell you. This is the way I organize lectures, and this is something that I manually do. And so I'll continue to post the slides right after lecture, even before the videos come, and so you get still versions of them. And sometimes that might be a useful thing to do. But the recordings would be, for those of you who have not been able to attend, or if you have attended and you want to look back something, then you could do that. And I keep a running list of the recordings that have come in this place, and I have a quick post usually that I would also post that same day. But this PDF file will have all of them when things happen. And so, for example, so far we have four of them, and I have started to edit the videos just a bit in the beginning. If there is something that needs to be cut out, I cut out if it was a silent period. But you have them that way. And so this will continue, and I wanted to point that one out. One thing I was not sure about was how much of a file size you can handle when you send an attachment in mail. And from yesterday's conversation with a few of you, I felt like there was too large a file size with the scans that I sent you. And so I was a bit concerned, but it looks like it probably is carrying or has got a capacity more than I thought it would. So I just wanted to point those things out before we get started with today's lecture. And so I am going to stop sharing this and instead share what I would like to do to discuss today. And let me see if I can find that portion, and I need to come, I guess, to my this, and this is the one I want to share for now. Stop share. And I'm going to share a new screen. This is what I want to share for today. But I don't see the other part. So I need to stop this for a while. Get to a place where I'm seeing this portion. All right, does everybody see now the place where I have the slide? Is that what I'm sharing? Can somebody say? I don't know why I'm not seeing.
Yep.
Okay, so let me do the next question now, question 2. So the next question I have, we have answered the cat and dog question. The next question I have is, I want to know how many languages you speak. And you would, I know for sure that you all speak English, and so that counts for one. And I want to know how many languages you speak. And so if I was going to design a Turing machine that accepts this one, I would know that 0 would not be an answer because I know you all speak English. So let me see how many languages each one of you speak. And you can have a generous definition for what you mean, you know, when I say speaking, how many languages you speak. If you know enough to communicate and carry you through, then that will suffice. Okay, very interesting answers. So I don't know if there is somebody who knows how to show how I can follow along the video as I present. That would be helpful. But for now, what I see on my screen, at least the way I'm sharing today, is just the slides. I think as far as I'm concerned, this would be okay. But do you see me? Do you see my video? Okay. All right, so we'll continue discussing Turing machines today, and I'm going to wrap up the discussion we have had so far. And by that, I mean the discussion on the chapter in Sipser's book, that is chapter 4. But first, let me give you some updates. So as you all now know, homework 5 is graded completely and the solutions are posted. And I have been able to send you scans, and you may find those useful when you look back at what James, the feedback, is my video on?
Yes, your video is on. We can see both your webcam and your full screen slides.
All right, perfect. Thank you very much. And if anybody needs to speak up like James has done right now, you can go ahead and do that. So they are posted. And so make sure that you look at the solution and make sure that you see how the feedback that James has given you means. And I think this might be a useful way to get your documents scanned when you try to submit later on. And so that's what I wanted to begin by telling you. There is a little bit of an overlap between what homework 5 had and what homework 6 is now asking. And homework 6, as you know, is due next Friday. And I wanted to at least point out those similarities and the reason for having those questions that were at least or on topics that were covered before spring break in homework 5, why they are coming. And so if you have been happy with how the scan looked like now, and if you are not going to be typing up your solutions, yeah, if you are not planning to write up your solution in a manner that would generate PDF automatically, then you can consider using that. And I hope that that video I posted was useful for getting to use that app in a manner that's free. And so here's how I am trying to see the relationship between what homework 5 was and what homework 6 now has. And what you see on the left is homework 5, and in a nutshell, all of the problems were on context-free grammars, and so you were asked to give, if you are given a language, to decide whether it was ambiguous or not, and if it is an ambiguous language, then how you can turn that one into an unambiguous version. The second problem had to do with generating grammar for a given language and to give an informal description of a push-down automata. And the third problem was about converting a context-free grammar into a PDA, and there were 2 problems on converting to CNF form, the Chomsky normal form, and the last one had to do with using the pumping lemma to show that a given language is not context-free. And among all this, so I think there was a little bit of a desire I had on my part on seeing where things would need a little bit more practice. So the first 3 problems in homework 5, in homework 6, do cover topics that are around context-free grammars, and there is some overlap there. Those color similarities that you see is to show you that. Problem 4, as I mentioned last time, had to do with the table filling algorithm to minimize the number of states in a DFA. And the other 2 problems, the last 2 problems of homework 5 are the subject that we've been discussing since we have begun having to do things online. And so there is a problem that would ask you to give an informal description for a Turing machine that decides a given language, and there is a problem that asks you to go a little bit deeper and draw a state diagram for that Turing machine that accepts a given language. So this is due next Friday by midnight, and you will submit it on Oswald, a PDF file, either scanned or typed up. And I would just want to encourage you to use the office hours this week with James, Monday and Thursday. I have an office hour this week also. And if we need to, after you've got a chance to look at the problems, if we need to spend a little bit of time in next Wednesday's class, we can do that also. And I just wrote a little bit of a note here on what we did with homework 5 on one of the problems that asked you to change it into a CNF format. There is a problem that made an appearance several times, and at some point we will tell you why that problem or that sequence of problems is called JH Lisp, and James will tell us the idea behind what's up with this JH Lisp. But I just wanted to point that one out before we get started with today's class. All right, I'm ready, and these were the two updates I have before we get going. Is there anybody who has got any question? All right, it looks like we are all set to go. And so what we did, the very last lecture, last time, when we looked at variants of Turing machines, was to see how much of a change would happen, or would the different extensions one can imagine to Turing machines if they were going to bring up any potential or any power to Turing machines that would make them more powerful in terms of recognizing broader class of language. So we saw three. We saw what happens when there are multiple tapes instead of a single tape, and that turned out to be an equivalent thing to using a Turing machine that has a single tape, which is a standard definition. We saw what non-determinism would bring to Turing machines, and similarly to see that there is, much like what has happened with NFS and DFS, non-determinism does not bring more power to Turing machines. And we finished off with a discussion that is slightly different in nature, that gives rise to other kinds of studies that are done around Turing machines, and the reason for calling them recursively enumerable language. Those languages that are Turing recognizable are equivalently called recursively enumerable. And so we saw that idea behind it and what it means to have an enumerator. And all three of these were ultimately, and in some cases we went down in a careful way, were entirely equivalent to the standard Turing machine. This is not the only models. There is very many variations. Some of these variations would come with things that look very much like Turing machines. And for example, instead of having multiple tapes, you could have multiple tracks, or you could have some other variations still, but within the notion or with this idea of machines themselves. And some of other notations are there that are very different when you look at them from the outside, but they are still equivalent. And then there is one thing that all of these models share in common, and it is access to unlimited memory, which is what Turing machine has. And when this thing is shared, they are remarkably equivalent with one another. And so we don't need to look for another machine to make the claim that we made in the beginning of this discussion when we first started, to say Turing machines are able to do what real computers can do today. This is where we stopped last time. And this is the place where I would like to begin by asking a question. And I know the large portion of this class is computer science class students. And so by having to take a class like the programming language, I'm not sure, and that probably is maybe a little late now to ask you, but I know that a good number of you take a course called programming language. So you are familiar with this idea of having different computer programming language, and I don't know how many times you have wondered if it is possible to make this claim. If somebody gives a program in some language, and Lisp would be one example. Most of you probably are not familiar with that language. That was why the heads up I gave you in that frequently occurring variation of a problem we had, JH Lisp. The Lisp there is the Lisp programming language, and you probably haven't heard of it. Or take another language like Pascal, which again was not a programming language that you know, or things that you know today, things like Python or C or C++. If somebody comes and poses this question and say, I have a program in this programming language, would you be able to write it in the programming language that you are able or familiar with? And so the question then becomes, is it possible to make the claim that any program written in one programming language can be written in another programming language? And it doesn't matter what programming language we are talking about. Is that statement true or false? And this one I would probably need a little bit of a participation from people. Is the claim that a program written in one language can always be written in another language when both of these are programming languages? So I've got people responding, and so they've got a yes and a no, and a yes and a no. And it looks like okay. So there is a good number of split here, and somebody has qualified the answer by saying theoretically yes. And let me be very clear and give you a definitive answer for this one. The question is not about practicality. The question is not about how friendly it is. The question is not about how easy it is. Theoretically speaking, if you can write a program that could run on a computer in one language, you can always write it in another language. And the idea and the theoretical explanation for it is to say, I can always compile one language to the other. If what you have written in one programming language could be compiled, then there is, theoretically speaking, a potential for us to compile it to this other programming language. In fact, if you were to study how compilers would work, they would come to a point where it becomes irrespective. That's what compilers would do. Try to have a representation that would be translated into a machine language. And so if you start from there, then you can work back up and write something that would deconstruct this one and write it in a language that would be possible. So the correct answer for this one is yes. But I understand what somebody may be tempted to say no, and you might have struggled if there is something that would support, functional programming, for example, or some other constructs. You may find it almost impossible to do. But theoretically speaking, regardless of how much effort you put into it, you can always write whatever was written in one programming language in another programming language. So there is a statement that can be made about equivalence of programming language. This is not going to help us very much, because we would now need a concrete or a precise definition for an algorithm, because all these programming languages that they have done, you can, at the end of the day, think of things that have happened and that could be called algorithmic. When you see this word, some of you might still thinking, there are some actions that we take, some data processing things, some things that are about conversions, about writing things and so on, that don't give you the flavor of an algorithm, but they are an algorithm at the end of the day. And that is the idea behind the subject I want to talk about today. So what is an algorithm? Is the question we want to answer. And I want to begin by acknowledging some things. And you probably have heard this one before you take a theory of computation class. Almost everybody these days now actually uses that word. And coincidentally, with the time we live in now, when things are very much data-driven and machine learning, an algorithm has become a familiar term. Lay people would use it. Oh, this was decided by an algorithm, you may hear. Or somebody may even, have been on a radio broadcast and tell you about music choices they made, and then they would tell you, oh, this was chosen by real people, by real hosts, not by an algorithm, they would say. Well, because an algorithm would make some selections about running things and seeing where people's location are and trying to determine what their favorite would be. And so the notion of algorithm has become more and more familiar with us now. But intuitively speaking, an algorithm is a collection of simple instructions for carrying out some basic task. And I think this is what would come to most people's mind. I want to tell you first that this notion is a lot older than computer science. We have the term itself, the origin of the word itself has got a lot of history that dates way back before computer science. So I want to give you a few examples. Gaussian method, you might have taken the linear algebra course, and you have even before you get to start to college, seen how a linear system of equations is solved. That's what Gaussian method is. The German mathematician Carl Friedrich Gauss that you see in this picture here came up with how you eliminate things, and they get more and more sophisticated. We have software tools that basically do that step now for a large metrics, but that's an algorithm. There is a step-by-step procedure that you follow in order to determine, unknowns in an equation. You can even go further back in time and look at people like Euclid, and you've heard of Euclid in many ways, and I'm showing here a picture that is the actual Euclid I'm talking about. Is not to be confused with another Euclid. And so Euclid of Alexandria, and that's a Greek mathematician, came up with, that was a long time ago, how to find the greatest common divisor. If you have two numbers, what will be the greatest common divisor for them? And so there is a step-by-step thing that you follow, and you might have run into writing a program yourself on how to do Euclid's method for having to compute the greatest common divisor. And something of that nature, similar idea, would be used for finding prime numbers. And that is also attributed to Euclid. In fact, finding prime numbers is a big, and factoring prime numbers is a big issue now, or a big problem now. And that's one of the things that you would encounter in cryptography if you care. So this notion was there. It's very old, and there is an intuitive understanding for it. And this could take us only so far. And one of the reasons, when I remember when we began this course, I asked it informally about survey, what are you trying to get out of this course? What do you understand by theory of computation? And there were so many interesting answers I was getting. But one of the things I hope you will begin to appreciate will be obtained, or you will be able to see that today, because this intuitive understanding of what an algorithm is, even though we have been doing this for centuries and we know what that means, is not going to be sufficient for us to have a deeper understanding of algorithms. And by deeper understanding of algorithms, I mean precisely the kind of questions that you were trying to answer with the equivalence of programming language. What does it mean? So the reason I was getting a yes, I was getting a no, I was getting a qualified answer for it, was to say that there is, what do you mean? What is it that would make whether this one is existing or not, and especially if we wanted to claim results around impossibility, then we need something that would be more precise. And this is going to be what I will tell you. And that didn't come as old as the notion of algorithm was there. It is, in fact, is a relatively recent discovery we have. And so I want to begin by Hilbert's problems. You might have heard computer science and many other fields these days, we always have conferences and people would come and talk about their latest and greatest works. But in 1900, Hilbert, he's a German mathematician, did make something that is considered one big famous kind of lecture in one of these congresses, and it happened in Paris. And he made a list of 23 mathematical problems that were challenging at that time. And his goal, his audience was the top mathematicians at that time, and he had this list of problems that he thought would be difficult to solve and posed them more as a challenge. One of the problems, his 10th problem in that list, goes about asking for finding the roots of a polynomial. And his question was formulated to say, to test whether a polynomial, and you all know what a polynomial is. It's got multiple variables and it has got terms that you add them together, and each term would have a coefficient, and something will be called a root for it when you find values for those variables that would make that polynomial equate to 0. That's what a root of a polynomial is. And so his question was, if I give you a polynomial, would you be able to determine, come up with a procedure that would find values for these variables so that are integers, so that they are roots? That means they would equate to 0. That was his 10th problem. He doesn't use the word algorithm in the way he described his problem and the way he stated it during his lecture, but what he says very much agrees with the intuitive definition of an algorithm I told you. Devise a procedure, a step-by-step method by which you will determine whether you will be able to find roots for the polynomial that are integral. And so this problem today, and by the end of this lecture, and you probably already know, we know the answer for this question. He posed that problem, but there is no algorithm that would do that task. And so the intuitive understanding of algorithms that I just told you, and the one that people were at that time aware of, would not be able to give an answer for this one, because it's asking for something that is not there for the intuitive understanding to be sufficient to give an explanation. This is true for other situations also in computer science. You might not have run into too many examples like this, but there are times when somebody would come and the result that they have is an impossibility result, a result that says this cannot exist. And that means it's not more about our ability, our cleverness, or how much we have become good at it. It just is not going to happen because it is impossible. And to be able to give an impossibility result like that, whether it is about approximations, whether existence of an algorithms, the more fundamental thing that is needed is a precise definition. And so it requires a precise definition, and that's why we will be doing. And this question, whether this algorithm exists or not, was answered in 1936. If you follow along in the book, and I'm sure you read, the chapter that we are on now and that we're going to conclude today is actually called the Church-Turing thesis. That's the heading of that chapter. And so there are two people that come. And this result came by a paper written by Alan Turing and Alonzo Church, they're called, in 1936. So this problem was posed in 1900. People were trying to come up with, to solve the 23 problems, including the 10th problem of Hilbert. And so this result comes and tells us that this is not going to be possible, and it lays a foundation. There are other people who followed up on that work and actually made that statement that we know today, that Hilbert's 10th problem cannot be solved by a computer. The thesis for it was done by the two people I mentioned, that the pictures of whom you see there. And the basic idea behind it, when it boils down, is to say the intuitive notion of algorithms that existed before this period, the ones that I gave examples like the Gaussian method or Euclid's method for finding common divisors, that's how we understood algorithms. That is equivalent to what Turing machines algorithms would do. That's the reason we're studying this theory course. They are saying basically the same thing. And the way they have approached this one, and the more like intuitive understanding for you to say is they approached the two worlds from different perspectives. So Alan Turing, the Turing that we have been studying so far, uses his machines with the control, with the tape, and with the configurations and the way we have been formally describing them in terms of tuples. That was a Turing machines perspective. What Church did was using some notational symbols. That's called lambda calculus. And so these two, what this thesis showed are equivalent. It's not going to be a very good analogy, but the analogy I would give you is like this. Think about regular language. What regular language were, the way we studied them and with the way we have seen so far, were expressed equivalently using finite automata and regular expressions. And when you look at them, and I have said this so many times now, but when you look at them, they don't look anything similar to one another. They seem very different things, but they were doing equivalent things. And I want to be a little bit cautious here. That is a good analogy to see. So much like NFS, where for regular language, you've got Turing machines for Turing recognizable language. Much like regular expressions, where another way to look at them, lambda calculus would be one other way. But these two are equivalent. And that gives an answer for having now to say, what do we do with Turing machines will give us a way for us to determine when things are computationally possible, when an algorithm exists or not. And I remember, I don't remember exactly who the student was when we were meeting in person. I got a question at the end of our lecture one time, and somebody asked me if we were going to be studying lambda calculus, and my answer was no. And this is probably the only time I will mention it. And this is a fundamental result that I would like you to know. So how did now, I've just kind of gave you more like an appetizer, but how was actually Hilbert's 10th problem now solved? Because we now know how Turing machines work. That's what I want to spend a few minutes on talking about one and digging a little deeper. So Hilbert obviously didn't think of in Turing machines terms. He was posing these problems because of their mathematical difficulty and because he saw them as things that would challenge for the rest of the century, was basically how it was. And so his tens problem, if we were now to turn it into our terminology, the way we are now understanding it, would go like this. So we've got a language, and we'll call that language D, and it is a language of polynomials that have an integral root. So if I define D in this way, D is all of those languages, all of those polynomials with an integral root, then his question in a sense would be asking whether D is decidable by a Turing machine. And so the answer we know is negative, and we are just about now to see, at least to convince ourselves that the answer is negative. But let's first contrast, and we'll contrast this one with being Turing recognizable. And you remember last time we ended up with that picture we saw, at least for the purpose of our discussion, at least for this course, our universe is Turing recognizable. And within there are problems that are decidable and problems that are not decidable. And we're just about to encounter one. We have already declared that it is not decidable, but so we will show that it is Turing recognizable as one of the things we would do. Before we get there, before we show that it's Turing recognizable and Hilbert's tens problem is undecidable, I want to begin by having a simpler problem. And then this is how CptS builds up the argument here. So let's first think of a language or a simpler formulation of that problem where our polynomial is restricted to be of a single variable. So generally speaking, our polynomial will have multiple variables. It will have terms, that will have coefficients, and they will be added up. That's what a polynomial would be. But let's have this simpler situation where we have just a single variable, our polynomial, and we'll call that language D1. And so we'll call the language that is made up of polynomials over a single variable that have integral roots, we'll call it D1. And so we want to see what Turing machine we can design to recognize D1. And here is our familiar way of putting what our Turing machines would be, and we are going to decide on how to decide on this language. And so our M1, now M1 is a Turing machine that recognizes the simplified language D1, that is a polynomial over a single variable that have integral roots. So it will take on an input the polynomial, and I'll in a second tell you what that symbol means. But for now, just think of it as an input, just like we write on input string W. That's how we have been describing things so far. On this input, which is a polynomial over a single variable, we're going to evaluate P with X set successively to be these values, 0, 1, -1, 2, -2, and 3. And so we're switching, if you notice, we're trying all integral values, basically. So the question we wanted to answer is whether P actually is a polynomial over this single variable and it has got an integral root, and therefore we don't want to try some other things. We want to try this to integers, but we want to be trying positive and negative, switching one at a time. And so we go forever, we continue in this fashion. So, and if at any point this polynomial evaluates to, I should have written to 0, then we accept. That means one of these, what we have been trying, is a root, is what it means. So if P has an integral root, then this Turing machine that we just described will eventually find it. It's just a matter of time. We're trying exhaustively all the integers that we possibly can have, and because it's just a single variable X, we are trying these values for X each time. And the moment we find it, we accept. If P does not have an integral root, which could happen, then M1 will run forever. And so this Turing machine now recognizes our language D1. So we can similarly present a Turing machine that recognizes the original problem, Hilbert's tens problem, when it is of multivariable. What will happen now is we will need to do this checking for every single possible variable, for every possible combination. So if I had 3 variables, I would say I would use these variables, values, integral values, 0, 1, -1 for x, similarly like that for y, similarly like that for z, and then in all of these combinations. So that might be an overwhelming number, but we can exhaust, we can enumerate all of those possibilities, try one at a time, and the moment we get, we will accept it. Because we are now not limited by how much we have to run before we accept it, we will say that this is recognizable still because we have a way to do it. So we can present a similar Turing machine, and we'll call that one M, that recognizes D. The question becomes different when we want to talk about decidability. And the answer we get for these two, for the simplified version and for the general version, are different when it is a decider. So we can convert the simpler one, M1, to be a decider for D1, because we have a way to calculate bounds within which the roots of a single variable polynomial must lie and restrict the search to these bounds. That bound, I did not write it here because I didn't want to make the slide overly complicated, but it is not very difficult. It is got, when I have a single a polynomial over a single variable, then there is a result that we can say looks at two special or extremal values in a way, one of the coefficients in the terms divided by another, and the number of terms we have. When we have these three things, the quotient and the product would give us a bound, which means now we're not going to be doing and running the machine forever, potentially, if it does have a root. So there is a bound. We can restrict ourselves to that particular range, and therefore be able to decide whether it's going to terminate or not. And so for M1, we are able to do that. That means when Hilbert's tens problem is reduced to a single variable 1, it is decidable because we can calculate these bounds for which we can limit our search. We have a result, and this result tells us calculating such bounds for multivariable polynomials is impossible. And the name of the person is not very important. This result comes around 1940s after the Church-Turing thesis that I told you. But I want you to know how people have come about and how the Turing machine has helped us now show an impossibility result. So this is where we are now able to say it's not a question of the power of our computer or how genius we have become in coming up with an algorithm. It just simply doesn't exist. Why? Because we cannot find such a bound, and therefore there is for limiting our search. And so our Turing machine that is going to decide this one doesn't have a limited thing that it can search for, and so it will run forever. So it's not possible to be able to decide this language. This answer about Hilbert's problem, the undecidability, the way we argue about it, is going to be the subject we will handle next. So there are problems that are undecidable, and how would we formalize them, and what kind of reasoning are we going to be able to say when this problem is not going to hold, where we are not going to be able to answer it. And so I hope by now, by running through this one, you have gotten a sense for how an impossibility result would be shown, and one particular example for where this has happened. So in some ways now, this has brought us to a good place where we would say how our course, our understanding, our study of theory of computation is going to turn in some ways. So we will continue to use Turing machines, but our focus from now on will be on algorithms. And so we were using Turing machines on our understanding that we have built on it to serve as a precise model for the definition of algorithms. And for that reason, we are going to kind of have a way to describe things and a way to think about Turing machines that would more guide us into having this algorithmic perspective. And we will rely on higher level description or high level description of Turing machine algorithms and follow a certain format and notation. And I want to begin by telling you that one, because that's how we will work on with Turing machines now for the next lectures and set of studies we will have. But before I say that, we have already been doing a high-level description of Turing machine algorithms so far. And all the examples we saw, for example, in last lecture, or the lecture before last lecture, was here is what the definition of a Turing machine is. but we were able to say, we saw only a couple of examples where we went to the extent of drawing state diagrams for them. That will be a very fundamental low-level description. And we want to be convinced of that. Then there is some value in having to deal with that type of treatment. But for the other examples we saw, we were satisfied with the high-level description. And we could still have a little bit of room in what we mean by that high-level description. And CptS kind of tries to describe between two, higher level and high level. And the way we will use them from now on will be to give something that will be at the highest level possible. And we'll need some way to describe things and some formats and notation. And that's what I want to begin to tell you now. So we will always assume that the input to a Turing machine is a string. This will probably make you feel like we just saw an example where you were telling me about having to decide a polynomial whether it is an integral value or not. I could imagine very many other problems that you have worked with that they don't look like strings. And in fact, you probably would rarely work with strings. But the question or the formality here doesn't make us any weaker. It's not an assumption that is too much to say it's not useful, because we can encode. And because we can encode, then we can treat almost any object as a string. And this is always possible. This is a place where you also need to be thinking more theoretically now. And there is value in having to think of them as strings, because it will be consistent with the study of languages we have been showing so far, with their relationship with other computational models we have seen so far. And so there is that continuity, but it's not going to be something that would limit its ability to be useful, because whatever input we have, we can always encode them into strings. And because we need to reason around this one and come back and give algorithms that would actually make sense, we can decode back. If an input was encoded into a string fashion, we can, for the purpose of how the results of that algorithm would be given, for example, Hilbert's problem, what the integral values for the roots of the polynomial, they will be formed in terms of numbers like that. So we can always encode and decode back. And both of these could be done by the Turing machine itself. So this is always possible. Our notation for having to encode an object O into representing as a string is going to come between this O, the object that we are encoding, and being delimited by these symbols less than and greater than. That's why you saw in the example I gave you in Hilbert's, or for the polynomial, the P was within these two brackets. That's a notation. That's a notation that is used in the book, and it's also fairly standard way to describe them. And so here is our notation. Our input is a string. Whatever the input was, we can always encode it. In fact, one of the things we would work out with will be to say how we would encode a particular object as a string. And the notation to show that for that particular object formulated as a string will be to use this notation. Maybe there is one question that probably would come right into your mind, is to say, what if I have multiple objects? And so we can have multiple objects that are inputs to our algorithm, and we could denote their encodings into a single string by having to just list them around. And so if I had k objects, O1 through OK, I can have an encoding that is a single string made up of all of these O's, right one next to one another. There is a potential, again, for a question to come to somebody's mind here. Does it have to be unique? So I may encode something one way, and somebody else may encode it a second way, and somebody else may encode it some other third way. And there may be some advantage. In fact, sometimes when you come to actual ways in which encodings are important, there is in fact a reason for having to do things in a way that would be helpful. One of the criteria, or one of the things you would want to consider might be, for example, how easy it is to be called back, or it could be about space, or it could be about understandability. So there are, all of these could be reasonable ones. And so for the purpose of decidability or not decidability, for the purpose of having to say something that is about complexity class, which we'll very briefly touch later on. For all of these purposes, it doesn't matter what that encoding is among the many that are possible. So encodings, it's good to know that they can be done in different ways. It's not unique, and there may be advantage over one over another, but it is not going to limit or it's not going to change the overall objective of what we have with describing Turing machine algorithms, because they are equivalent. It won't matter. The other 2 points I want to tell you here is more about formats, how they are described, and I'm going to be running out of time in a second, so I should probably be a little quicker, and I have only one slide to show you. So we have seen how Turing machine algorithms are described, so we will use indentations to show things that happen within more like loops, and we try to break them down into steps. So I just realized that we have, so here I have a quick example, and you will see this example. If you need to run into another class, you can, but let me just use 30 seconds to finish this one off, for you to see an example of an actual problem that you can formulate a Turing machine algorithm for. And let's say the problem that you have is to determine whether a graph is connected. And here I have a quick example of a graph. A graph is nodes linked by edges, and this particular graph is not connected. It has actually 3 pieces. But if it was connected, if this lower portion, for example, was what was given to you, what will be a Turing machine that would decide it? What algorithm would it look like? And here's the algorithmic description for it. I have an input that is an encoding of the graph, and will select a node from graph and mark it, and then repeatedly see if we can reach to all nodes that are not marked by successfully following these edges. And if all of them are marked by the end, then we will say this graph is connected. If there is a node that is left unmarked, that means it cannot be reached, then we will reject it because it is not connected. So at least it gives you a very quick flavor of a problem that is familiar to many of you and probably easy to understand. And here is how the Turing machine that decides it looks like, at least the format of it and how it is presented. All right, we have run out of time. I have to stop here, and hopefully you were able to follow me along. And our topic for next time will be undecidability. Any questions for those of you who are still around? I know there is a good portion of you, 45 of you around, 44 of you around. Anybody has got a quick question? If you have a question on homework 6, Wednesday's class will be a better time to ask, and make sure that you use the office hours. But if you had a question on what we discussed today, and it's a quick one, I can answer now, or you can use Oswald to follow up for his questions. All right. I hope this you were able to follow along. So I'll stop here, and I'll see you next time.